Okay, before we get started today, did anyone have any questions from the lecture from Wednesday? Or maybe I should ask, did you guys watch the video that I posted? Yes. Okay. Okay. Yeah, let me know if you have any questions. Okay, so today we're going to be talking about host heterogeneity in the context of infectious disease models. We'll be introducing ideas about heterogeneity, explaining what those mean, and thinking about their consequences as well. So by the end of today, you should understand what we mean when we say host heterogeneity. We're going to be talking especially about risk structure as a particular form of heterogeneity. So hosts may be at high risk or low risk of disease transmission. We'll be characterizing a transmission matrix and a contact mixing matrix to help us to distinguish between high and low risk groups. And then we'll talk about ideas of assortativity. So this tells you about individuals who are more likely to interact or have contact with similar individuals. Okay. So all of the disease models that we've looked at so far are all homogeneous in the sense that there's no variation between hosts. There's no intrinsic variation between hosts. In other words, there's no variation in their susceptibility to infection or their risk of infection or their risk from disease. So, you know, their risk of dying. We haven't actually dealt with death from disease yet either. But none of those models have any of those effects in. Obviously, this is a gross simplification. We saw, even with this simplification, with that very first Kermack-McKendrick model from back in the 1920s, that you can still fit an SIR model to data and it'd be pretty accurate, even without that host heterogeneity. But there are various cases where that heterogeneity can be really important. So, for example, if you really care about disease-associated mortality, and we think about something like COVID-19, that was highly associated with age. So older people are at much higher risk than younger people of dying from COVID-19. Likewise, people who had comorbidities as well were much more likely to be at risk of disease. Also, things like risk of contracting or passing on an infection. If people have lots of contacts, again, COVID-19, people that were sort of service workers or working in hospitals had the contact with a lot more people, or much higher risk of infection than someone who's, say, able to work from home. Also, things like sexually transmitted infections. There are various groups in the population are at higher risk, especially, you know, people who come into contact with sex workers. It's much higher odds of getting a sexually transmitted infection. So there are many cases where we want to capture these types of heterogeneity because it may tell you something about maybe where you want to target your interventions, and it may tell you about the effectiveness of those kind of targeting as well. So we're going to learn all about that today, and we're going to focus, like I said, on risk structure. So what we're going to do is we're going to take our homogeneous population of hosts, so everyone is identical, and then we're just going to split them into two groups. Those who we're deeming at high risk and those low risk. So in the context of, say, an STI, you might think of this as people who have a high sexual contact rate and people who have a relatively low sexual contact rate, or people who have multiple partners and people who have one or very few partners. This doesn't have to be limited to STIs, though. Like I said, it could be something like people who work in, say, hospitality or in hospitals as well, that maybe have contact with lots and lots of people, and people who work in, I don't know, who work from home most of the time, I guess, who might be in the low risk. Okay, so we're going to assume that these risks are all, or these differences, these heterogeneities are all based on behavior. This doesn't have to be the case in general, but these are not intrinsic host factors. By intrinsic, I'm meaning like something at, say, like a genetic level. So this could be related to their sex, it could be related to their prior health, or any sort of genetic component. So it's nothing intrinsic, it's all about their behavior. We're also going to assume that all other heterogeneities are irrelevant. Yes?
Yeah, I wanted to ask if we consider the other part of differences, it's going to be the same models and calculations.
Basically, yeah. Going down the behavioral route allows us to do a few extra things because we're going to be talking about mixing behavior and contact patterns. But by and large, yes, you can break the population down into different groups. It's still that kind of same compartmentalization that we would do. So say if it was by sex, we might break people down according to sort of male or female. If it as by health. It might be people that have comorbidities or don't have comorbidities. It doesn't always have to be binary as well. It could be age. So a lot of these models might be age structured, but have like bins of age groups. You might have like 0 to 5-year-olds, but 6 to 10, and so on. Okay, any other questions? So we're going to assume also as well there's no disease-associated mortality and no immunity from infection, just because it reduces the number of equations. So if we were to have a transfer diagram for our population, we're going to have individuals who are susceptible in the high or low risk groups, H and L. We are going to have individuals who are infected in the high or low risk groups, and individuals can move from one of these categories into the other, either through infection and they can move back into recovery. So we're assuming here as well, there's no change in behavior. So if you're in the low risk group, you're always in the low risk group. Crucially, these two are not isolated from each other. Okay, at the moment, it looks like they're isolated. Really, we've got transmission occurring. So these high-risk hosts are going to affect the transmission rate, this infection rate of these high-risk individuals, but they may also affect the infection rate of these low-risk individuals and vice versa. So these low-risk individuals can affect the infection rates of low-risk individuals and likewise for high-risk individuals. So this is assuming that they're not completely separated. So these red dashed arrows here are just indicating that these rates here of infection depend on both the IH and IL classes. Okay, so let's write down some equations. So we've got an SIS model. We're going to have 4 equations because we've got 2 classes now. Let's call these DSH dt, DSL dt, and then likewise we're going to have DIL dt and DIH dt. So previously, with our very simple SIS model, we had something that looked like this for our, don't write this down just yet. We had something like this. IH. Right, we would have had something like this. Okay, and this is just if infected high-risk individuals can infect the low-risk individuals. Okay, but now we need to account for this heterogeneity. So now we need to account for both differences in transmission, beta, but also infection coming from our high-risk class as well as our low-risk class. So I'm going to call beta HH the rate of transmission from high-risk individuals to high-risk individuals. And then beta HL is going to be my rate of transmission from low-risk individuals to high-risk individuals. So both types of individual here can infect these high-risk susceptible hosts. Likewise, for our low-risk class, beta LH is going to be the transmission rate from high-risk individuals to low-risk individuals, and beta LL is the transmission rate from low risk to low risk. And then because this is a simple SIS model without any demography, our I equations are just going to be minus our infection classes change at opposite the rates of our susceptible classes. Okay, so beta IJ is the transmission rate from individuals in the J risk class to those in the I risk class. Everything else is similar to what we've had before in our SIS model. Any questions? Okay. Let's keep it as simple as possible. So we're going to assume that the proportions of individuals in each class are not going to change. So in other words, the number of individuals ni in Si plus ii, where I is just lowercase I is an index that can either be H or L. The number or proportion of individuals, we can scale it number or proportion, it essentially doesn't matter here. As we've seen before, we can scale back and forth between numbers and proportions. Here, this ni is going to be fixed. So what does that mean? Well, that means, as we've seen before, we only need two equations here, because as soon as you know one of the either sh or ih, then you know the other one, because nh is a constant, and likewise, if you know sl or il, you already know nl because that's a constant, so you can work out the other one. So we don't need four equations, we only need two. And I'm going to stick with my equations for the infected classes, just because we're going to be working towards our basic reproduction number. Okay, so what does this look like? Well, we have our infection terms. For IH, we can have beta HH times by IH plus beta HL times by IL. Now, previously we multiplied this by SH. This is now going to be NH minus IH. And then we have a minus gamma IH on the end. Our equations for IL are going to look very similar, except for the fact that we'll be changing our indices. Okay, so before we just had one transmission rate beta, right? Now we've got four transmission rates, and one simple way to represent them is in a 2x2 matrix. So I'm going to call beta now this matrix, which is composed of these transmission rates. Note that here, the way that I set this up, the rows are the transmission rates to the high-risk class, and the columns are the transmission rates to the low-risk class. Conversely, the columns are going to be the transmission rates from the high-risk class and from the low-risk class. Okay, so whether you're looking at rows or columns, affects whether it's transmission from or transmission to. Yeah. Okay, so these transmission matrices can be very helpful because they can tell us something about, and they're often referred to as who acquires infection from whom matrices. So sometimes you'll see this written as a WAIFW matrix. Who acquires infection from whom? Sometimes they're abbreviated for that. And these matrices are a convenient way of capturing this mixing, as well as ultimately finding important quantities like R0. So what do we expect this matrix to look like? Well, for one thing, these high-risk individuals, sorry, you go. Yeah.
Quick question. So beta HL, it's high infecting low or low infecting
Low infecting high. So second one infecting first one. Yeah. Okay, so what do we expect? Well, they're high-risk individuals. Well, they're high risk because they are more likely to be experiencing infection. That's what we said at the start, due to some sort of behavioral practice. Maybe they have more friends. Okay, so we should expect our total transmission rates to our high-risk group. So in other words, beta HH plus beta HL, in other words, that first row should be greater than our second row. So beta LH plus beta LL. So this is just first row. The sum of this should be greater than the sum of this, right? Because they're high risk by definition. If it was the other way around, you'd end up with this slightly perverse scenario where your low risk individuals had a higher transmission rate to them than the high risk individuals. So it doesn't really make sense to call them low risk. So there are no intrinsic differences between these hosts. That was an assumption that we made in terms of their susceptibility to infection. It was all about just their behaviors, their contact rates. So because of that, we should also expect this matrix to be symmetric. In general, that's not necessarily going to be true, but what I mean here is that this beta HL and beta LH should be the same thing. This is just basically saying it's all down to contact rates, and those contact rates are symmetric. So you can think of this as being, what is the rate, we'll talk about this in a moment, but the contact rate of these individuals, high and low risk, well, a high risk person meeting a low risk person is the same as a low risk person meeting a high risk person. What else might we assume for this matrix? Well, we might also expect in many cases to see something called assortative mixing. Now, assortativity is all about individuals who are similar, preferentially mixing with individuals who are similar. Now here, similarity is all about contact rates. So we're assuming, therefore, if this matrix is assortative, then high-risk individuals should be more likely to be in contact with high-risk individuals and low-risk individuals in contact with low-risk individuals. So if we look at our beta matrix, and I'm going to scale my text size here, we should expect the term, the top left of how we've structured this matrix, beta HH, to be the largest. Beta LL, I'm going to do it a little bit smaller. Hopefully we can see the difference in these sizes. Beta LL should be smaller because these are high-risk individuals contacting high-risk individuals. So that should be our highest rate of transmission, right? These low-risk individuals meeting with low-risk individuals should be somewhat moderate. And then if we've got assortative mixing, then we're basically saying high-risk and low-risk individuals don't come into contact with each other that much, or their risk of transmission between them isn't that high. So I'm going to make these two pretty small. So largest, moderate, and smallest. This is not always the case. Okay. This is just one particular scenario. This kind of thing tends to work well, especially with sexual contact networks, because people who have more sexual contacts are more likely to come into contact with people who have more sexual contacts. So they tend to have a higher risk of transmission, and they tend to associate more often with other individuals who have multiple sexual partners, just because they're moving around and having more sexual partners. Okay, so we can actually make some further simplifications. We're doing lots of simplifications here, but we're doing that because these models otherwise can be quite difficult to analyze. One thing we can do is, remember when we had just our scalar transmission rate from our standard SIR model or SIS models, we could construct or deconstruct this transmission rate beta into the product of two things: a contact rate, which we call C. Remember that we talked about this when we discussed density dependent and frequency dependent transmission. So we have a contact rate C, and then we can think of a probability of transmission per contact, which we could call P. So thinking about it this way, we can do the same thing with our beta matrix here. We can think about decomposing each of these terms in the matrix into a contact rate and a probability of transmission per contact. Now, if we assume that this risky behavior is all about just contact rates, risk of transmission here is all about contact rates and isn't anything to do with actual behavior. So again, in the context of something like a sexually transmitted infection, it's all about contact rates, say, and we're not assuming any differences in terms of things like condom use. So if the probability of transmission per contact is the same for everyone, in other words, there's no heterogeneity in that probability there. The heterogeneity is only in the contact rate C. That means we can write down a contact matrix. So our contact matrix, what's that going to look like? Well, I'm going to start with our transmission matrix beta. And we're going to divide it by our probability of transmission per contact. So that's just like taking this equation here. And if we also divide this by the contact rate, C, the baseline contact rate C, that's going to give us a matrix that tells us something about the proportion of contacts and where those contacts occur. So what does that matrix look like? Well, I'm going to use rows with the same subscripts that we had before and the same ordering. So now these rows, so row ij is the proportion of individuals in group I, proportion of their contacts that occur with individuals in group J. So individuals in the high risk class, row HH of their contacts, that proportion of their contacts also occur with high risk individuals. Individuals in the high risk class have a proportion row HL of their contacts with individuals in the low risk class. So you can also note here that the sum of the rows must equal what? Yes. So we could actually simplify this further. We don't need 4 parameters here, we actually just need 2. I've left it in there just to emphasize that these are that these correspond to HH and HL and so on. But we do only actually need 2 parameters here. Okay, so what's the use of doing this? One of the nice things about setting up these contact matrices like this is that we can calculate something called the degree of assortativity. So the degree of assortativity is telling us, this matrix, call it capital Q, is telling us the extent to which, or I'm sorry, Q is not a matrix, Q is this measure here. It's telling us the extent to which individuals mix with individuals who are like that. So how assortative is this matrix? We're not going to go into the theory behind where this comes from, and you don't need to memorize this, but it turns out that if we have G groups, so here we just have 2 groups, but in general we can have as many as we want. So let's say we have G groups. The degree of assortativity is given by 1 over G minus 1, so 1 over the total number of groups minus 1, multiplied by the sum of our eigenvalues of this matrix. So there'll be G eigenvalues because it's a G by G matrix, minus 1. So eigenvalues are going to be important here. If you've done anything, I guess we've talked a lot about eigenvalues and matrices, and eigenvalues tell you something about like long-term behavior. They can also tell you something about in these infectious disease models where we have these contact matrices, they can tell you something about what is driving the dynamics. Okay, so your eigenvalues here will tell you something about the degree of assortativity. It also tells you something a little bit about what's driving the dynamics. So let's think about some examples. So think about what happens if our matrix, our contact matrix, is highly assortative. So in other words, Q is approximately equal to 1. Before we go on to that, what would that matrix look like? If this is highly assortative, what's this matrix going to look like, or be close to? Don't worry about trying to work it out from here. Just think, what does it mean for this to be highly assortative?
You only have the 2 eigenvectors, but it's going to be like an identity matrix.
Yeah, so these the rows have to sum to 1, right? And if it's highly assortative, that means like matches with like. So most of the proportion is going to be here in this row and here in this row. So this is going to be close to 1. This has to therefore be close to 0. This has to be close to 0. This has to be close to 1. So you're right. It's going to be pretty similar to an identity matrix. Not quite there, but let's call it something like this. Say our matrix now would look approximately like, let's call it 1 minus epsilon 1, and then epsilon 2, 1 minus epsilon 2, where these epsilons are much less than 1. So this is what our highly assortative matrix will always end up looking something like this, because your proportion of contacts are mostly with individuals who are similar to you. There is no universal highly dissociative matrix. This Q here tends towards -1 over G minus 1 when we have something that's highly dissociative, but this depends on things like the proportion of individuals who are in each group and things like that. There's no uniform way of making there's a uniform way of making a highly assortative matrix, and in the extreme, when you only mix with individuals that are like yourself, this is the identity matrix. But there's no sort of uniform thing the other way around, especially if we have many classes. So if you think about there's only one way to mix with individuals that are completely like yourself, but if we have many groups, there are multiple ways to mix with individuals who are not like yourself. So there's an infinite number of ways to make dissociative matrices, whereas the extreme assortative matrix, there's only one of these. You might be wondering, okay, to what extent does this actually matter? Well, this here is a model showing instance of AIDS per 1,000 individuals in the population under these two assumptions of assortativity and dissociativity. So this dark one here is highly assortative, so Q is approximately equal to 1 here. So this is highly assortative. And when we have these highly assortative matrices, we end up seeing these multiple peaks. So underlying this model is actually assuming that there's a relatively small high-risk community and then a much larger low-risk community. Again, that's kind of common for many sexually transmitted infections. So what happens here is initially, the dynamics, this epidemic here is predominantly among high-risk individuals. So they see this initial sort of outbreak, first of all. But then that starts to, this sort of a trickle in, if you like, into the lower risk population. And then you see a bigger wave afterwards in the lower risk population. So that's because, we go back up to this here, most of the initial transmission is being driven by this term up here. This is really driving things because it's much bigger than these other terms here. Eventually, there's a little bit of trickle into these groups here, and then there's an epidemic in the lower risk. If you had many different classes, you would actually see this sort of moving its way through these different classes. So that's what you tend to see with assortative mixing, at least if it's highly assortative, that you can see these sort of multi-peak epidemics as it makes its way through these different risk classes. If you have things that are highly dissociative, like this dashed line here, so this is a case where Q is approximately to -1, so this corresponds to being highly dissociative, or at least it's -1 over G minus 1. Here there were just two groups, so this just tends to -1. Okay, so what does this look like? Well, here we actually see a much bigger peak than in either of them, and it occurs still relatively quickly. This is because high-risk individuals, they're not really infecting other high-risk individuals directly, they're going through low-risk individuals, but low-risk individuals are having high contact with high-risk individuals. So in some ways, it kind of breaks down this idea of who's high risk and low risk. But it still kind of, it then has this kind of like weird tail to it. It doesn't kind of follow our traditional epidemic. Okay, so it's still having a bit of an effect here. Okay, so how are we doing for time? Okay, not too bad. Let's then think about our basic reproduction number. So let's think about how we can find R naught in our matrix. So remember, like when we had our SIS models before, say, dt is equal to beta Si minus gamma I. And then to find R naught, we would look at when is 1 over I di dt, which is equal to beta S minus gamma. When is this greater than 0? And assuming that S is approximately equal to N, rearrange this, you get beta S over gamma has to be greater than 1. This was our R naught. So we just looked at the per capita growth rate when rare, right? We can't do that now because our beta is a matrix. So we can't take that same approach as we did before. We have to think now about our eigenvalues of this matrix, because those eigenvalues tell you something about those growth rates, what's dominating growth rates. So let's just take a numerical example because it's easier to work with. I'm going to assume that my high risk group has beta HH equal to 10. This is 10 times bigger than my low risk group. And then the off diagonal terms, I'm going to assume they're 10 times smaller as well. That is 0.1. We also need to think about the NH and the NL, in other words, the proportion of individuals in our high risk group and the proportion in our low risk group. I'm going to assume that a high risk group only make up 20% of the population. So most individuals, 80% are low risk. And for simplicity, we can just non-dimensionalize this model, which is equivalent to just setting gamma equal to 1. Okay, so our recovery rate, we can rescale time according to our average infection period. That's essentially what that does. We don't really care about the recovery rate here. It's just a numerical example. Okay, so let's think about how we can calculate some upper and lower bounds for R naught to start with. We can do this by considering the sum of the transmission rates weighted by the proportions in each group. So we can think about transmission that's occurring from our high-risk individuals to other high-risk individuals or to low-risk individuals. And those high-risk individuals, because they have the highest transmission rates, overall the sum of those is the highest transmission rate, that's going to give us an upper bound on what R naught can be. Because anything that's coming from low-risk individuals is going to be at most equal to what the high-risk individuals have, but typically lower. So what do we mean by that? Well, let's think about our upper and lower bounds. Our upper bound, which I'll call R naught U, and lower bound R naught L. The upper bound, well, let's take our transmission rates for our high-risk group. So we have beta HH. And we're multiplying this by susceptible hosts in our high-risk category. So remember, what we're doing here is we're just taking this term here, dividing it by the recovery rate, because that's going to give us essentially our R naught upper, if you like, if there was no equation here, if it was just all based on this. And oh, sorry, no, that's not quite right. We're taking this term and this term. We're assuming that everything's being driven initially by this high-risk class, right? So that's going to give us our naught for the upper bound. And we're going to multiply this by, well, IH is going to be very small. So we multiply by NH, likewise IL would be very small. So we multiply by NL. What does that mean? Well, let's go back down to these sums here. So we take beta HH and we multiply it by the proportion of the population that is susceptible and high risk, which is going to be NH in the absence of disease. We're going to think about transmission from high-risk individuals to low-risk individuals and multiply that by the proportion of the population that's low risk. And then we divide this by gamma, our recovery rate. So this is just saying, okay, early on in the infection, if everyone's high risk and infected, if everyone who is infected is high risk, what's going to be the R naught coming from those individuals? So how many individuals on average are these high-risk individuals infecting? Yes.
Is that divided by gamma?
Yes. So how many individuals do we expect one high-risk individual to infect on average? That's going to give us an upper bound for our R naught. And for our lower, well, we do the opposite. I'm going to say, okay, what is the transmission rate? What is our transmission rate from our low-risk class to our high-risk class, and from our low-risk class to our low-risk class? Again, weighted by the proportions of individuals in each of those categories. So this is just a numerical calculation. Above, our beta HH was 10. Our NH is 0.2 because it's 20% of the population. Our beta LH is 0.1 and NL is 0.8 because it's 80% of the population. Our gamma was 1. This gives you an R naught of 2.08. And for our low risk, when we do a similar calculation, we get an R naught of 0.82. So note here that if we just had the population composed of these low-risk individuals, it's not enough, or if rather, if our low-risk individuals are our initial sort of infected population, there's not enough new infections coming from this class to sustain the epidemic because our R naught is less than 1. For our R naught for the upper bound here, basically expected number of individuals infected by these high-risk individuals is above 1. Yes?
Is it a coincidence that the sum of both of the R naughts, like the balance, is an integer? Just wondering.
Just because I've chosen these values.
Yeah.
Nothing special about it in general. It's just a coincidence. Okay. So that's providing an upper bound and a lower bound. To actually calculate R naught, we can use our next generation matrix, which we met a couple of lectures ago. So we use our next generation matrix here because our population is structured. Remember, we did this before with our SEIR model. It turned out in that particular case, because there was no demography, it didn't matter. But we learned the method for that. Here, our population is structured, and it will matter. And it will matter because there are different transmission rates. Okay, so what's our J going to look like? So our J matrix, our Jacobian for the infected classes here, is going to be, and we're doing this when our population is at its disease-free equilibrium. So almost all of our susceptible hosts, almost all hosts are susceptible. They're either high risk or low risk. So we have NH instead of SH and NL instead of SL. When we substitute that into our Jacobian, we're going to get beta HH NH minus gamma, beta HL NH, beta LH NL, and beta LL NL minus gamma. So we construct our next generation matrix by first splitting this into matrices F and V. And those matrices F and V are going to be determined based on what is new infections versus just movement between classes or loss of infections. I'm actually just going to skip down to the bottom first of all here. So we're going to define these matrices F and V. So J is equal to F minus V. And our F matrix is going to be what? Well, remember, this F matrix is just new things, new infections in this case. So we go through this matrix and we pick out all of the terms that correspond to new infections. Note terms, not elements of this matrix. So this term here, everything that has a beta in it, in fact, corresponds to new infections because it's transmission, right? So we only take things out of this matrix that have new infections. So we have beta HH NH, beta HL NH, beta LH NL, and beta LL NL. And our V matrix is just going to be gamma, 0, 0, gamma. Right? So remember, it's not the element, it's the term. Does that make sense? Yeah? Okay, let's carry on with this numerical example. So our Jacobian for the numeric example is going to be 1, 0.02, 0.08, and minus 0.2. So there's nothing particularly special about this numerical example. It's just here to illustrate the method a little bit easier. Our F matrix and V matrices, again, if we plug the values in from the previous slide, we'll get 2, 0.02, 0.08, and 0.8 for our F matrix. And our V matrix is just going to actually be the identity matrix now. Okay. Can anyone remember how we calculate our next generation matrix? So we have this F matrix and this V matrix. Can anyone remember the next step?
You want to multiply F and V inverse?
Yep. So we find V inverse. V inverse is just going to be what? Yep, it's the identity matrix, so it's exactly the same. So we just do F times by V inverse in our next generation matrix. This, which in this particular instance, but not in general, obviously, is just going to be F because we're multiplying F by the identity matrix. So we need to find our dominant eigenvalues. The dominant eigenvalue of this matrix is going to be pretty close to 2. The reason being, you can kind of see that these values here are very, very small. That means this is pretty close to a diagonal matrix. So this R0 is going to be approximately equal to 2. This next generation matrix, what we're really doing is we're ultimately looking at stability of our disease-free equilibrium. Our next generation, take a step back a sec. When we look at our eigenvalues of our Jacobian, we need both eigenvalues to be positive. Sorry, we need at least one of these eigenvalues to be positive in order for our disease-free equilibrium to be unstable. That means we're moving away from it, right? When we do our next generation matrix, it translates this eigenvalue problem to another eigenvalue problem where our threshold for stability is not at 0, it's now at 1. That's just part of the linear algebra, it translates it to that. We know that R0 being greater than 1 or less than 1 is our threshold for an epidemic taking off or dying out. So all this is doing is it's translating this problem from this Jacobian into this next generation matrix. It's telling you as well the contribution from each category to the next generation of infections, if you like. That's what's called a next generation matrix. The other cool thing that we can get from this is by looking at this dominant eigenvalue here, we can, well, actually, no, sorry, I'm getting ahead of myself here. Note that our upper bound we had was just above 2. And our actual R0 was about 2. So this is telling us that the high-risk group is basically driving those early dynamics because everything is pretty much coming from them. We can also see that by looking at our dominant eigenvectors, the eigenvector that's associated with our dominant eigenvalue. If you calculate this, it ends up being, the normalized version at least, is approximately 0.94, 0.06, which you can rescale to be about 15 to 1. That's exact. I should put this here as a, I don't know if that's exact actually. I'm going to call this V1. Little bar underneath it. I can't, yeah, my mental arithmetic's not right. It's going to be approximately 15 to 1. Why is that interesting? Well, it's telling us that the early growth of our epidemic, this first entry is going to correspond to our high-risk individuals, because that's how we structured our matrix. And this is low-risk individuals. This is saying that our high-risk individuals are going to, at the start of an epidemic, make up 15 times more of the infectious class than our low-risk individuals. That's why this R0 here is so close to our upper bound of R0. It's because our high-risk individuals are driving all of that early transmission. We saw that as well in this graph here, right? High-risk individuals are driving that early transmission. It's not a super large peak, but pretty much everyone here is high risk. Pretty much everyone here is low risk because it's a highly assortative matrix. So this eigenvector here, this dominant eigenvector is telling you early on where is going to be most infection. High risk group or low risk group. This could be 15 times higher. So roughly 94%, that's the other way of just looking at this vector here, the normal scaled one, roughly 94% of infections during the early stages are in that high risk group. You can see why looking at these types of matrices can be really useful from like a public health perspective. So you can tell you, okay, only 20% of the population is high risk, but during the early stages of an epidemic, 94% of infections are in the high risk group. Therefore, we should be targeting things towards the high risk group preferentially because they are the big drivers of transmission. Keen for the next lecture. Okay. That's just about it today. I just wanted to say a final note about how this is a very simple example, obviously, of a risk structure population, just to introduce these ideas to you, and that this is not the only type of host heterogeneity. We talked about, there might be other types of heterogeneity in terms of things like susceptibility or risk of mortality. So I just wanted to finish by thinking about what do they look like. So think about maybe our susceptibility. What might that look like if we have heterogeneity in that instead? Well, this is still going to be our beta term. So if we go all the way back to our model here, this beta term is telling us, okay, what is the rate at which these susceptible high-risk individuals are becoming infected? And it encapsulates things like the probability of transmission, as well as contact rates, transmission from high-risk individuals, susceptibility of those high-risk individuals as well. So one way we could break this down is if we instead assumed, unlike we did here, where we assumed there was a contact rate that was varying, if instead our contact rate was fixed, so say it was just equal to some constant C0, we have our mixing rate or mixing proportion that we had before, not mixing rate, mixing proportion, rho ij, that was in the matrix we had before. But now we'd be multiplying this by some varying probability of individuals in class J infecting individuals in class I. So that probability might vary. This might, for example, be due to differences in practices. Again, if we think about sexually transmitted infections, just a little bit easier, this might be, say, individuals might be high risk because they don't use condoms. So you might be able to stratify the population according to some behavioral characteristics like that. If we think about something like, say, COVID-19, we might have an age-structured population or people structured by comorbidities. So there's no mortality in this model, but in principle, we could include mortality terms. So for example, we might have mortality by group, which could be, say, if alpha H was the mortality or per capita mortality rate for individuals who are infected in the high-risk group, we might have a different mortality rate for these groups, with our high-risk group having a higher mortality rate than the low-risk group. So we can incorporate this type of heterogeneity if we think about disease-associated mortality as well. It is exactly 20 past. So you're free to go. Have a great weekend. If you have any questions, to answer them. Oh, and there is a Jupyter notebook as well on Canvas for you to have a little bit exploring what these dynamics are like with these risk structure populations. Okay.